Can you tell us what drew you to cryptography research and how has your perspective of the field evolved since you started?
So you want my origin story. There isn't one thing that drew me to cryptography. But I think initially when I came to Berkeley, I wasn't thinking about crypto. I can think of a couple of things. For instance, I read, there's a wonderful book called The Mathematical Gardener, which is a tribute to Martin Gardner. And in that book, there was a paper by Shamiri Vespen Edelman about mental poker. And just before he started at Berkeley, I read that book, or in particular that chapter, and that certainly showed me that there is a lot to the area. In terms of scientific developments, one thing that happened roughly when I was starting, maybe my first semester, is the result of Goldreich, Mikhail, and Wigderson about zero knowledge proofs for all of NP, which was both extremely simple. It had a very nice trick and had far-reaching implications, and that definitely made me pay attention. And so these are two events. Another, in general, I would say I started real research in cryptography sort of twice, in some sense. Once I was working a lot with Amos Fiat, and then at one point we met by chance at a Berkeley cafe. So this is a Berkeley story. The Berkeley cafe, we met David Sharman. We started discussing the ideas that later on led to the work on untraceable electronic cache. So that's sort of one path, and it was a pretty, it had a lot of elements that were to define my work, the field, etc., like anonymity, the application of zero knowledge, what happens when you abuse, to sort of abuse prevention in the sense that you're punished for abusing. The idea there was if you spend twice, then it's zero knowledge as long as you spend it only once. If you spend it twice, then you're exposed. So the punishment is your exposure. So that's one direction. Another direction is I started working on digital signatures with Mori Jung when we came up with the notion of universal one-way hash functions. And actually, I happen to have another origin story, and that's this book, The Code Breakers. So The Code Breakers is a book, it's a thin book, as you can see, done. And I think that when Diffie and Hellman, for instance, started their work on cryptography, let's say about 10 years or so before my time, uh, that's essentially all the information they had, all the public information they had about cryptography. It has a lot of details that were unknown at the time. I think it was published in the late 60s. I think it's the first place where the breaking of the Enigma was exposed. Not the full one, that came later on, but the fact that something like that existed. And the fact that it's a big industry. Remember that cryptography was hidden, it was under the surface. There weren't conferences on cryptography. There weren't people talking. There was a famous Shannon paper, of course, but between the Shannon paper and, let's say, the work of Diffie and Hellman, there weren't a whole lot of papers in the area, a whole lot of papers published. On the other hand, there was a lot of work, confidential work, classified work done in cryptography. Anyway, so reading this is also one of the motivating factor that led me into the field.
Okay, great. Your research often links cryptography with complexity theory. Can you talk a little bit about how these fields mutually inform and benefit each other?
So here I have to quote Shafi Goldwasser, A Match Made in Heaven. Um, so, um, so it's so the basic idea, the sort of the fundamental idea of cryptography is that you have to use some computational hardness to your advantage. It's true that there are some things. There is the area called information theoretic cryptography, and you can do some wonderful things there. For instance, secret sharing would be one such example. But for most things, you can prove that if you want to have if you want to do anything, so to speak, non-trivial, I mean, anything, then you do need to use the idea that there are hard problems and an adversary cannot efficiently, the information is there, but the adversary cannot efficiently extract it. So therefore, the connection is very natural. So cryptography is a consumer of computational complexity, of computational hardness in this case. On the other hand, what experience showed us is that cryptography creates a lot of interesting complexity. I mean, just one wonderful example is the one on is the PCP theorem that started, or the whole model of PCP started from has cryptographic origins, where the question is, what do you gain in terms of can you do things if you have two provers and one verifier, and the two provers do not talk to each other? What can you gain from cryptographic point of view? For instance, can you get rid of computational assumptions? That was the questions that Benor, Goldwasser, Killian, and Bigderson asked in the late 80s, and gave the answer. Not only asked, also gave the answer, but they also raised the question: is okay, so we have this model with two provers. What can we do with it? And that led to a huge development in complexity theory, to the in particular the power of two provers, the PCP theorem, and lots of other things. So, so the developments of both areas are really tightly related. And I mean, obviously, after such spectacular development, it's a little hard to follow on. So I'm not sure I will be able to give you many other examples, but I think that that's quite enough.
You've been instrumental in developing critical concepts such as non-malleability and broadcast encryption. Could you talk about the core ideas behind these concepts and some of their real-world applications?
Okay, so non-malleability is the idea that you're trying to strengthen the notion of the protection that encryption gives you. Encryption, and sometimes it can be other things, but let's talk about encryption. So if I'm sending a message, is a sealed envelope really the right metaphor? I mean, well, it is a very good metaphor, but notice that there is the question of, if I see one encryption, can I create another encryption that is related to the original one? And you can view it as a positive thing. And that is exactly what happens in fully homomorphic encryption. Fully homomorphic encryption, you have you have a message, and you can do all sorts of you have an encrypted messages, you can do all sorts of operations of it and end up with a function of the original message, which is again encrypted, without learning anything about the original message. So that's a positive case, but often we view it as something negative. We don't want, if I'm sending somebody, let's say, think of an auction, I'm sending a bid, and I don't want other bids to be related to my bid. I don't want them to, let's say, take my bid and put one less than that bid or anything like that. So that's a case where I do want the encryption to be the encryption to make it impossible to create another encryption that is related to my encryption. And that's exactly what non-malleability is. Sort of the opposite of fully homomorphic encryption.
So perhaps provide an example of when a seemingly difficult problem is beneficial in cryptography.
So we usually think of computational hardness, that the problem is hard to compute. We think of it not as good news. Think of it as bad news. Oh, this is so difficult. In cryptography, we are looking for such problems where it is hard to compute on the average from certain distribution. We consider this a good news. And one famous example, going back to the beginning of public key cryptography, is factoring composites into primes. And that is, as far as we know, a hard problem, not the hardest problem, but it's a pretty computationally hard problem. Not as hard as we would like, but still. And also not resilient to quantum computers, but this is a hard problem. And it would have been very nice if we had a polynomial time algorithm for factoring, but we do not know of one. And the good news is that this means that we have a whole bunch of good crypto systems that can be based on it. As long as we don't improve on our factoring algorithms, and we don't have a quantum computer, which means changing a computational model, then we have a very nice cryptographic scheme. So the bad news, the fact that we do not have a factoring algorithm, a polynomial type factoring algorithm, means that it's good news for cryptography.
Great. You've been involved in the development of methods that verify human users of computers that led to the notion of CAPTCHA. I'm curious to hear the initial motivation behind this research, and also if you could comment on how this has evolved as a technology in the age of AI.
So the motivation was quite clear. I was thinking, how do you know? How do you force? You want? How do you make a user pay attention to your service? That is, I think at the time there was sort of a meta search engine. There were several search engines, and the idea is, why not ask all of them? The question is that good or bad, and it's probably not so good if you want people to pay attention to your own search engine, and you don't want it to be part of some larger schemes without your permission. And that's actually what started me thinking about this direction. And the question, the idea is quite obvious, I would say, and I'm sure that several people had it as well. And the idea is to create tests where humans excels and the computers do not. At the time, well, I'm not sure I was exactly up in sometime in the mid-90s, where the examples I gave were really state of the art. But at the time, I did think of again, going back to the example of factoring, that it would be wonderful for a problem to be part of this sort of test, what led to CAPTCHA, because it would mean that there will be a lot of attention will be given to it, and therefore it will develop. Exactly what happened with factoring algorithms, how they developed from RSA until today. We have both in terms of algorithms, we have better algorithms and in terms of systems. So I thought that it will be very interesting if this is what will happen to some problem in AI. Now, as far as I know, nobody now claims that they indeed have a way of generating problems automatically that can be tested, and where humans are doing better than machines. As far as I know, none of the systems is secure in this sense. But I have no claim or thought that it's impossible to create a system that somehow it's complete to the AI, that somehow it's AI complete or anything of that sort.
Okay. In your opinion, what are the most significant emerging threats to cryptographic systems? And what research directions are you most excited about to address them?
There are many. I mean, you could think of regulations. There is the famous expression cryptographic wars. The question is, I mean, you can ask, can governments regulate it? Should governments regulate it? How they should regulate it? And I wouldn't say that the fact that we do have, let's say, crypto available right now, it wasn't inevitable. I don't think it's inevitable. And the fact that it will remain so is also not inevitable if society and various countries, people, organizations wouldn't rally. It may be legislated out. Now, of course, you can start saying in this case, only the bad guys would have crypto, etc. If crypto is outlawed, only the criminals would have crypto. And the good, of course, the emergence of cryptocurrency also means to a large extent that it will be less motivation for doing it. But again, who knows exactly what governments will want in the future, what restrictions will be. Nothing is clear cut. So that's the possibility. That's one threat. Another threat is that science, we will learn that crypto is much harder than we think right now. Let's say breaking some of the popular schemes, it's certainly a possibility. Of course, the emergence of quantum computers will break others. It may break others. So I wouldn't say that our job is done here, and not at all. So that's in terms of threats. And the question had a second part.
Yeah, what research directions are you most excited about to address these threats?
To address these threats, I'm not sure, but I would say all of so. Okay, so there are things that what I mentioned includes both science and also governments and companies, etc. Let's not absolve various companies. So I don't. But again, what I mentioned it's not a pure scientific issue. So I cannot say, oh, if we do this, if we do that, if we find so and so, then we won't have any problems. That's just not true. I can tell you about various developments in the field that I'm excited. Of course, work certainly. So we had 10 years ago, we had the Simon's meeting on cryptography, and this is cryptography 10 years after. I should have worn my shirt, my 10 years after shirt, a t-shirt that we got at the workshop. So there, I mean, we have tremendous progress, both theoretically and in practice. For instance, the idea of proofs of zero, what's so-called zero knowledge proofs. I'm saying so-called not because there isn't a thing, but the term zero knowledge is used in a wrong manner. Usually, they just mean succinct proofs of again in the cryptocurrency arena, and they're at a scale that I wouldn't have imagined 10 years ago. Just tremendous developments. Theoretically, the issue of obfuscation that was unclear 10 years ago, whether it's a thing or not, of indistinguishability obfuscation, it wasn't clear. The jury was sort of out. I mean, maybe there was some direction, but since then we have great results of Jinlin and Sahai that tell us that we can base it on pretty standard assumptions. And so, at least theoretically, indistinguishability obfuscation is a notion that we can work with without making wishful thinking. So, without making it into a wishful thinking style, it's relatively conservative. I wouldn't say that it's practical yet, but who knows? Never say never.
Right. How do you envision the role of cryptography as evolving in society, particularly in the realm of issues like privacy and surveillance?
So there is, let's say, a notion of differential privacy that is of cryptographic origin. Obviously, it's not exactly crypto, and that is a partial answer, at least. It's not panacea. It doesn't fit in all cases, and a lot of the work done can be used to mitigate the surveillance society, the surveillance capitalism. Here, the issue is motivation. Is there a marketplace that can support these things? And again, it wasn't inevitable, but this is how things work. The answer right now is no. We give away a lot of information to various companies, various corporations, without an essential need. It's not that they need it in order to provide us with good service. You can argue that a lot of the things they give us do not require them to learn so much about us, but there is a little not enough is done in order to prevent it.
Okay. So you mentioned Simons Institute a few minutes ago. So you've been a frequent visitor to the Simons Institute. How have these experiences shaped your research and views as well as influenced collaborations?
So both, I've been in various programs here, not here at the Simons Institute. I'm at home right now. So as any meeting, I mean, any meeting when you're bringing in the top people is obviously quite an experience. So you're both learning the state of the art, and you're able to hear the thoughts or peek into the thoughts of the leaders of the field, and that's always wonderful. It really, and I mean, and even more, I don't know if more important, but as at least as important is that you see all the young people, and I'm so happy to see that there's so many young researchers who are interested in these things and making huge progress. I mean, it's certainly not an old man's craft, this area. So Simons, of course, the Simons Institute allows you to participate in these things, and this is wonderful. Can I think of anything particular that shaped me? No, I mean, I'm working along these lines all those years, so it's a little hard to say, oh, this is the particular thing. But certainly when I hear lectures, I really like lectures on machine learning and AI, and this is again one of the subjects that is being discussed in at Simons. That's very intriguing for me.
Okay. And as part of your career milestones, what were some discoveries which you personally felt were quite rewarding?
I don't want to offend any of my discoveries. So I can tell you one discovery, one very early discovery that was actually done in Hawaii in 88 was done, published in 89. And it's a very simple idea. The idea is how, and it's related if you want to go back to what I mentioned to Goldreich, Mikhaili-Victors on the result of zero knowledge. The question is, can you do it based, what is the most general assumption you can base your zero knowledge proof on? And the idea, my idea there was that you could do it simply. I mean, what they assumed is that you have a function that has unique openings. So if I give you y, there is a unique x such that f of x equals y. And if f satisfies certain properties, then they could base it on that. And my result back then was you can actually base it on a more general assumption, on the assumption that pseudo-random generators exist. And a pseudo-random generator takes a short seed and stretches it into a long seed, and the long string looks exactly computationally, it's indistinguishable from a short seed. This is a computational pseudo-randomness is a notion developed by Blum, Mikhaili, and Yao. And what I was able to show is that using actually a technique from originating from complexity theory, that you can do it based on the assumption you don't need the unique opening. You can get rid of that assumption. You can base it on the existence of pseudo-random generator, which in turn can be based on any hard to invert function. So that was both simple and I wouldn't say far-reaching, but certainly it said, oh, we don't really need uniqueness. We can get rid of one of the things that looked essential in that work. You can actually get rid of it. So that I think at the time I was very happy with this sort of result because it also showed me that that you can really get that general results are not beyond our reach, and even can be quite simple sometimes.
Moni, thanks so much for being here and doing the Polylogues with me. It's delightful to have you with us.
Thank you. Enjoyed it.